Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of the show, bringing another really awesome guest for you today involved in science, technology, creating a better tomorrow for all humanity. Today on the show, we have the honor of being joined by Les Johnson. Les is a physicist, an author, a space technologist who most recently served as chief technologist at NASA's George C. Marshall Space Flight Center. And over a really distinguished career with NASA, he played central roles in developing advanced space propulsion systems, as well as pioneering technologies designed to expand humanity's reach well beyond Earth's orbit. He has led and contributed to multiple interplanetary technology demonstration missions, including works on solar sails, in-space propulsion, deep space exploration architectures. And in addition to his NASA career, Les is an extremely accomplished author, both of popular science and science fiction, known for making some extremely complex space science accessible to broad audiences. And his books, both fiction and nonfiction, explore the scientific and philosophical dimensions of the future of humanity in space. He's also a prolific public speaker, advocate for space exploration. Les holds a master's degree in physics from Vanderbilt. He did his undergraduate work in physics, also Transylvania University, conducted research in plasma and material sciences, and his academic foundation, no doubt, laid the basis for this really long-standing commitment to bridging theoretical science with practical space engineering. And we're honored to have him with us. A lot of really cool topics to get into today. Les Johnson, thank you so much for taking time to come on the show.
Oh, thanks for having me. I'm glad to be here.
Great to have you. Really great to have you. Would like to start off at the beginning, Les. I was reading all about you to get ready for this show, and I find it kind of interesting that you grew up in, I believe, Ashland, Kentucky, which was a hub of all things chemistry back in the day. But you were very interested in physics, and you told some stories about how some of the physics classes you went into in undergrad, you were the only student there. Take us back a little bit to sort of when your excitement for all things physics got started.
Well, it really got started at an early age. In fact, I was about 12 years old when I decided I wanted to be a scientist and work for NASA. Didn't really know what a scientist did at age 12, but I figured you had to do that. No, for me, I've always been fascinated with the stars. I remember as a young boy going outside looking at the sky. My parents woke me up on July 20th, 1969. I was 7 years old, probably wearing footy pajamas in bed asleep. To watch Neil Armstrong land on the moon. And then my older sisters let me stay up late with them, I don't know, a few years later on Friday nights when we would tune in a very grainy picture and watch reruns of Star Trek. So from that point, I was hooked and started reading science fiction. But Ashland was a fantastic place to grow up in the 60s and 70s. It was an industrial town. You mentioned chemistry. Absolutely. There was a steel mill, several chemical plants. It was kind of, industrial mid-America kind of town. But the people there were very supportive. I had teachers who knew what I wanted to do. They saw me reading science fiction books in class when I finished homework assignments. Had a lot of friends who tell me now they knew in middle school that I'd end up working for NASA. But it was a wonderful small town. Not many people had aspiration to go work at NASA there. Had a great physics teacher in high school, Mr. Larry Lowe. Got to give a shout out to great teachers that I've had. Mr. Kenner for chemistry. And that all launched me on to go to Transylvania, which is one of the two better private liberal arts colleges in Kentucky. And I really have to credit my mother for that. My father was deceased. He died when I was in middle school. But she said, Les, you can specialize in physics later. What you got to do is get a good liberal arts education. You got to learn a little bit about everything. And so that kind of launched it all. And I owe a great debt of gratitude to the wonderful people in Ashland for being so supportive.
Awesome. Awesome. And then, from there, you move down the road to Nashville, to Vanderbilt, where you do your master's work in physics. Your thesis is on particle beams and lasers and surface properties of molybdenum. And the fascinating thing here, aside from just sort of the work that you were doing, is you're doing this at a time where really two things are happening. One, President Reagan's Strategic Defense Initiative is sort of in the works in terms of high energy lasers and particle beams and all that stuff. And we'll touch on that a little later on when we get to things like Golden Dome and what's happening nowadays. But I couldn't help but run across this report that you were involved in. Now, this is really amazing. You're at Vanderbilt. You're preparing a report for the Air Force Office of Scientific Research, which also gets kicked over to something known as the Ballistic Missile Defense Organization, which is ultimately what becomes the Missile Defense Agency, all about basically what happens to the properties of certain materials on intercontinental ballistic missiles. Now, I got to say, this must have been, thrown into the middle of all this during your master's must have been something else. And again, I would love you to take us back to what was happening in the early 80s, because this is personally, I remember President Reagan's speech on Star Wars when it happened. So take us back to this period, if you would.
Oh, sure, sure. Well, this was the mid 1980s.
Yeah.
I started it at Vanderbilt in 1984, and this is during the time period where Ronald Reagan really was making it known, about quote the evil empire, and that we needed to be aggressive in trying to confront or contain the Soviet Union. And he started the Strategic Defense Initiative in that time frame. But my thesis work spins into that in an interesting way, in that it was all funded by NASA. I was working on my master's degree under Dr. Norman Tolk, who is still in Nashville, was professor emeritus there at Vanderbilt until just a few years ago. But when I started, he was like the young Turk, aggressive new, professor research group guy. And it was on the surface properties of molybdenum. And the reason for that is we were trying to characterize different elements and materials that went into the tiles on the space shuttle, because the shuttle was fairly new then. It was in Earth orbit, and when it went into shadow in nighttime, it glowed. The tiles on the shuttle glowed in ultraviolet and a little bit of visible light, and they didn't understand what was happening. They knew what was in an Earth orbit: atomic oxygen, electrons, ultraviolet light, all these other things. But they were concerned that this was going to cause erosion and damage the tiles and be a threat to the shuttle program. So they were funding research out of the Marshall Space Flight Center in Huntsville, Alabama, was the materials science group. And my professor and we got a grant. And so I was doing work trying to figure out and understand, simulating the low Earth environment on these materials to see if we could help figure out what was causing the glow. And that involved hitting them with little particle beams and using laser spectroscopy to look at what comes off the surface. And that was great. I really enjoyed doing that. And then as I was wrapping up my master's degree, there was a job opening at NASA Marshall. And I'll get to how this ties into SDI in a minute. There's a story. Everything with me's got a story.
I love it.
I'm a storyteller. So they have a job opening, and Huntsville's only about 100 miles south of Nashville. So I applied. I got an interview. So I drove down and got my first look at the Marshall Space Flight Center here and interviewed in the materials lab. I went back to Vanderbilt, went home for Christmas, was supposed to hear after the first of the year. I was going to wrap up my degree and get out by May. So I was starting to look for jobs, and I get back to my apartment in Nashville, and there's a letter from NASA. So I open it. It's one of those letdown letters. Sorry, we didn't select you, right? So I was really bummed because I knew the guy. I thought we had a good rapport. I thought he liked my work, right? So I was really very disappointed that I didn't get the job. But Vanderbilt in that day, you had to put a resume on file in the graduate office when you were getting ready to get your master's or your doctorate. And so I had a resume just on file at Vanderbilt. And over Christmas, an aerospace company from Huntsville, General Research Corporation, had gone to Vanderbilt looking through soon to be graduate technical resumes. And they flagged mine and asked me if I'd be interested in interviewing for a job at GRC, General Research Corporation. So I went back to Huntsville and interviewed for the job, and it was to work on Reagan's Star Wars, the Strategic Defense Initiative. And so I interviewed. They said, well, you worked with low energy particle beams, a few electron volts, very low energy stuff, and low energy lasers, milliwatt kind of lasers. But we need to have somebody look at weapons grade particle beams, million electron volt beams,
Right.
Million times more energetic, and high energy lasers with, megawatts instead of milliwatts. So that's like 6 orders of magnitude. And there aren't many people who do that. You can learn. So you want a job? And so I said, well, sure. And they offered me really good money coming out of school. And so I actually started working for them part-time while I was still a graduate student in Nashville. I worked about 10 hours a week, and most of that was just reading reports to get ready for jumping into the job when I came to Huntsville. So as soon as I finished up all the work and got the degree, I moved to Huntsville. And that report you mentioned grew out of a contribution I made to the effort, very minor contribution while I was still a graduate student. And then I really got into it when I was in Huntsville, and I was at GRC before going to NASA for about 3.5 years. And there are a lot of reports and that I worked on there. But it was all about space. It wasn't NASA. My heart was in civil space, but anything space had my interest. So I was learning about spacecraft, how they're designed, the environment of space, and oh, by the way, how to destroy missiles.
Right.
So it was interesting.
I could believe it. Again, I love when it's obviously all declassified now, but I love when you find these things out on the internet. Like, my goodness, like that must have been a fun first project right out of college. But yeah, and we'll come back to SDI and directed energy and stuff like that a little later on, because we've touched on some of those topics on the show. But I know I'd love to, again, so you get to General Research Corporation, and then again, for everyone listening, sort of, this is a sort of one of the historic defense contractors that it ultimately, I think, becomes part of AT&T. But a lot of really interesting work there. And before we get into one of the areas, solar sails, which you spent a lot of time on, one of the first papers that you're involved in, or first projects on sort of these advanced architectures, is in 1998, something called PROCEDS, or Propulsive Small Expendable Deployer System, which, and again, I'm going to butcher this, but it basically involves these electrodynamic tethers from one rocket ship to sort of sling another ship sort of around the Earth, doing these orbital maneuvers with the Lorentz effect. I'm going to shut up now, but it's kind of cool. And I know it shows up a little later on, sort of some hybrid concepts with the solar sails. But again, okay, so they were like, Les, you're going to work on this concept here. How did this project fall in your lap? As the first thing, hey, this is an idea. Let me work on this one.
Well, that was after I went to NASA, and just real briefly, I liked my job at GRC, and it was going well, but I had another opportunity to interview for a job at NASA, which is really where I wanted to work. And I took that opportunity, and this time I got hired. Yay.
Cool.
And the fellow who didn't hire me retired only about 5 years ahead of me. And whenever I would see him at work and we were talking, I would always remind him, you didn't want to hire me. So, but we were good friends. We were good friends. It was my way of jesting with the guy. But no, here's what happened. I started working in the Advanced Projects Office. It was called Program Development at the time at NASA. And it was looking at what we would be flying next, future payloads for the shuttle, space lab missions, which are self-contained labs that flew in the cargo bay of the shuttle. Were flying, and there were lots of science missions to be done there. And I was a physicist, so I was supporting the science groups. But there was a project that was funded to fly called the Tethered Satellite System. And I was put in the group that was working on that. It wasn't my idea, and it was right before its second flight. The first flight had a glitch, and the second flight flew from the shuttle, and it was partially successful. There was an engineering problem with the wire, but basically they deployed out of the shuttle a 12-mile long braided wire that was insulated and had a 500 kilogram, 2.2 pounds per kilogram, about 1,200 pound satellite at the end of it that was provided by Italy. And it was to study the ionosphere, where all the electrons are in high low Earth orbit. And the interesting thing about it is that when you have a wire moving through a magnetic field, it gets a voltage drop across it. And that's the way we generate electricity in a power plant. If you go to a hydroelectric dam near where you are, or you can't go in and see a nuclear power plant, but the same way they work there with steam, the falling water in the dam turns a turbine, which is basically turning wires around a big magnet, and that generates a voltage, and that creates the electrical current that then flows into our homes and lets us have this interview right now and powers the world, right? So a wire moving through a magnetic field generates a voltage. Well, that's an interesting physics, interesting thing. But if you think about the Earth, it's a big magnet, North Pole, South Pole. And a wire moving through the magnetic field gets a big voltage across it. So this did, it was about a kilovolt, about 1,000 volts. Well, in the ionosphere where it was flying, there are lots of free electrons, because what happens is the sunshine takes that faint atmosphere and it strips electrons off the lightweight elements that are up there. So you get all these free electrons, and you have a voltage drop, which means you have a positive end of the tether. All those electrons are attracted to that positive end, okay? And if you have a way of kicking them out at the other end, you can get a current flow through the wire. And that's what they were doing on the tethered satellite system, is they were generating power and studying how that interacts with the environment up there. They generated about 1,000 watts, about a kilowatt. That's a lot of power. Interestingly enough, that energy has to come from somewhere.
Yep.
And where it came from was the velocity of the shuttle. So it basically slowed it down a little bit and caused its altitude to drop. So as I was looking at that, I said, you know, you could use this as a propulsion system. What would happen if we turned the current around and made it flow the other way with an outboard power supply, like a solar panel or something, so that instead of getting the natural voltage drop, you flip it, have the positive end of the wire be at the other end. So I did some calculations and figured out I could do that with a fairly modest power supply. And when you do that, instead of slowing the spacecraft down, you speed it up, which means you increase its altitude, okay? And if you phase, when you flow the current through it, depending on where you are oriented relative to the Earth's magnetic field, you can change your orbit inclination. So you could go from around the equator all the way to a polar orbit. You could raise your altitude or lower your altitude. And here's the benefit. You don't use any fuel. You're just using sunlight and the environment of low Earth orbit. So I thought, well, this is pretty cool. So there was an opportunity that came along called Future X, and it was to demonstrate new kinds of spacecraft propulsion. And most people were thinking rockets, different kinds of rockets, this and that. So I asked my management, this junior person, fairly junior, and remember, I was working with a bunch of Apollo veterans. So these are people who had built the Saturn V. They were nearing retirement. I'm the younger, in my 30s, guy who's joined the group at that time. And I describe all this to them, and they thought, well, that almost looks too good to be true, but if it is true, then it looks really good. Why don't you, we'll let you write the proposal. So I got a team together, wrote the proposal, and darn it, won. It was a good experience. And we developed a smaller version that wouldn't fly on the shuttle. It would fly on an expendable rocket, 12 miles long, wire with a small satellite, not 500 kilograms, more like 25 kilograms, I think, if I remember correctly. And it was to demonstrate propulsion so that you could raise or lower your orbit and demonstrate this as a propulsion system. So that's a long-winded answer with lots of physics. I hope I didn't lose the listeners, but it's an interesting way to do propulsion. Unfortunately, it has never really caught on. And that's because you have this long wire, there's a really good chance you'll hit something else in orbit. Right. And there are a lot of spacecraft up there right now. And so there are a lot of strict rules about flying these in orbit. I really think they still could be used safely. And since they don't run out of fuel, there are a lot of applications that are available for that. But no one's really developed it and used it since then.
Yeah, but it's still it served as the basis for your, again, a lot of what comes next in terms of, you thinking more about so-called propellantless alternatives to chemical rockets, and sort of this is where um, a major theme in your work, namely solar sails, begins. And again, this is something that you've been working on and thinking about, from sort of the material science side to ultimately how you make these things smaller, and the CubeSat work and all that. But could you take a little time, because I know this is a concept that goes back a bit, and some will even say, Kepler thought about this stuff back in the 1600s, looking at comets and all that bit. But what is the history? I mean, introduce what a solar sail is first and
Sure.
foremost, and a little of the history of when NASA began thinking about, hey, we can sail around the cosmos instead of using all these fuels and other stuff. We'll be quiet. We won't tell Mr. Musk we're talking about this, but talk a little about the history there, and then we'll get into some of the more advanced designs that you came up with later on.
Well, I don't think this will be a competitor to Mr. Musk because it's not a rocket and you can't ever use it to get it off the ground. So,
Right.
and we're far away from using it for people, and I'll explain why.
Sure.
One of the things I learned working on the ProSEDS, the tether experiment, is that space is not just a big empty place. And
Mhm.
I think there is a worldview in the space industry that all the interesting stuff is somewhere else, and you have to get through space to get there and survive it and just put up with it. And I look at space as an energy resource and a resource in many, many ways. It's just very diffuse. It's very, it's not all concentrated like you get in a rocket fuel or a nuclear reactor. And so I mentioned, getting power from the Earth's magnetic field and generating current. Well, the sun is constantly putting energy into the Earth and into the
Mhm.
solar system in two primary ways: sunlight, okay, and the solar wind, particles, protons, helium atoms, things like that. So, light has an interesting property in that it has no rest mass, which is bizarre, but it's one of those quirks of quantum physics. But it does have momentum, and it is also a quantum mechanical effect. And what that means is when light reflects from something, it acts like you're playing pool and your cue ball hits another ball and knocks it, right?
Mhm.
Or if it hits something and bounces back. So light, when it reflects from something, actually pushes on it, but it's a very, 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 very small push. So small you don't feel it on the ground. It's very hard to measure on the ground. But you can calculate what that is. And just to give you an idea of how little force it is, if you have two football fields of area, on a bright sunny day, low humidity, the sun's overhead, you're on the equator, you get the same force of sunlight as you get from holding a quarter and a nickel in your hand. Okay, so it's really not much. But when you get out into space where there is no air, you get well above Earth orbit, so it's vacuum of space, and you're not in a gravity well, you're in deep space, and you deploy a large, lightweight, highly reflective film, think aluminum foil, only about, I don't know, 100 times thinner, maybe 10 to 100 times thinner, lighter weight. Not thinner, but lighter weight. And it'll move because the light reflecting on it is going to push it. So in theory, you can use that to propel a spacecraft. And the beauty of it is, it's never nighttime when you're in deep space. The sun's always shining when you're close to the sun. So your acceleration is constant. It doesn't stop. And the difference between that and a rocket is when you use up all your fuel in your rocket, you just coast. You can't go any faster. You've reached your terminal speed. A sail will keep accelerating. And I give an example. If you deploy a large solar sail, and I'll talk about how big these things have to be in a minute, on a spacecraft, and you use the same weight spacecraft, and instead of the volume used to pack the big solar sail, you pack it full of rocket fuel, and you say we're going to have a race. If it's a sprint, the rocket is going to win, right? You hit a button, the rocket's going to ignite, it's going to be out of sight in seconds. But in about a minute, it'll burn up all its fuel and it'll coast at whatever speed it reached. You look at your sail and it's not going to look like it's moving at all. You come back in a week and it's moved some and it's moving at a faster rate. But after a
Mm.
period of time, depending on the size of the two spacecraft, maybe a few months, my sail because it's constantly accelerating, will pass the rocket and keep
Hmm.
going faster and faster. So it's a classic tortoise and the hare kind of story in deep space. Now, the sail materials, NASA first started thinking about it in the 1970s
Okay.
at JPL for a
Hmm.
rendezvous with the Halley's Comet. It was going to be the Halley's Comet rescue rendezvous mission.
Hmm.
But their ambitions were far greater than the technology at the time. Spacecraft were heavy. You didn't have the smartphone computer revolution miniaturizing electronics yet. You didn't have composite materials making things lightweight. And as a consequence, to get the thrust you need to move a heavy spacecraft, you have to have an extremely large sail. Okay? Because the force of sunlight is constant. I'm going to use one bit of math here. F equal ma. Force
Hmm.
equals mass times acceleration. If the force is constant, if you want a large acceleration, you have to have a low mass, right?
Sure.
And so you just can't with older spacecraft. So that mission was shelved. And we waited until really the small spacecraft revolution that began in the late 2000s with CubeSats
Yep.
and cell phones, and everything got lighter weight. And then suddenly it became feasible to build sails that are still big, but not enormous,
Hmm.
that could actually propel a spacecraft and move it through space.
Hmm.
Now, the history of the field goes back. Really, my understanding is the first person to really mention it as a propulsion system or something was Tsiolkovsky, the Russian
Okay.
space scientist. But he didn't understand the mechanisms and all that because they hadn't measured light pressure and quantum mechanics was still not even really known at that point. I became aware of it in a science fiction novel that I read in high school by Larry Niven and Jerry Pournelle, and it was called The Mote in God's Eye. And it was about aliens coming to Earth in big light sails, were their spacecraft that were propelling them through space. And I remember reading that book, and I had the opportunity in, I guess it was the late 90s, because of that tether experiment. I was asked to go to NASA JPL, the deep space folks for NASA, and be the lead for propulsion, looking at a follow-on mission to Voyager, and that
Okay.
how we could create a spacecraft to leave the solar system and have it travel 3 times faster than Voyager. And so in all the trade studies, we ruled out everything that existed, and I started looking at things that were advanced, like nuclear propulsion, and I put in the mix solar sails, tethers, everything else, and a solar sail looked like the best option. So
Hmm.
that really gave birth to the era of funding for solar sail work that I was involved in that began around the year 2000 and has continued off and on since then. We had a flight in 2010 of a
Hmm.
small sail, which I can describe a little bit later, and another flight in 2022. There's one in Earth orbit right now called the Advanced Composite Sail System. And then there's another mission that is being studied that was originally one I led called Solar Cruiser, but it's now got a new name, and I don't know what the name is, that'll fly maybe in 28 or 29. So
Okay.
the technology is still alive and well and moving forward.
And yeah, I mean, let's we can continue along those lines because I know you wrote this piece on the CubeSat revolution, and you're
Yes.
mentioning there's been several projects, and then just because you were mentioning Halley's Comet just then, you also wrote this piece on. I mean, it's I guess it's a separate project, but the what is known as the Near Earth Asteroid Scout project, which also involves CubeSats, and I'm not exactly sure if that involved any of the sail concepts, but could you talk a little bit about sort of what happened in that time period? Because again,
Sure.
as you're saying, these things keep going and you get into the later membranes and sort of the hybrid concepts again. Where is this going? Obviously, we're not ready to jump on the sail yet and go to Proxima Centauri,
Oh,
but
I'm ready. The
me too.
technology's not ready, though. That's the
Right.
problem.
But
Um,
where are we now with solar
yeah, yeah,
sails?
yeah. Well, I did the math and I figured out that this is early on, that in order to build a solar sail, not a laser sail, which came later,
Right.
that could be capable of traveling to another star in a reasonable amount of time. And I said 1,000 years. And listeners might think, well, that doesn't sound very reasonable to me. You have to compare that with what rockets do. The Voyager spacecraft are among the fastest we've ever launched. They're out of the solar system. If they were pointed in the right direction, and they're not, they would reach the closest star system, Proxima Centauri, in about 72,000 years.
Hmm.
I don't consider that to be practical. I'd like to get that down to 100 years or less, and I think that might be feasible, but 1,000 sounded good to me because we have written records going 1,000 years back.
Mm.
I just recently got back from the Czech Republic, and they have churches that were built 600 years ago, right?
Sure.
So they have a sense of time that's a little different than we tend to have in the Americas. And long-term projects, those took generations to build. So I said about 1,000 years. So I calculated you would need a sail that's a square kilometer in area and weighs very little, high strength, very thin, and there was no material at that time. This is around the year 2000 that could sustain its own weight, as it were, in under tension at that size. So I said it would have to be made out of unobtainium because we didn't know what it would be.
Right, right.
But then I backed that up and I said, okay, we're going to have to demonstrate ever larger, lighter weight sails. We better get started. So we started a project called NanoSail D, and it was a 10 square meter solar sail, okay, deployed from a small spacecraft called a CubeSat, a 3U. So it weighed 3 kilogram spacecraft, very lightweight, in Earth orbit. And we deployed a 10 square meter solar sail that was 2.5 microns thick, which is the thickness of your hair, looks like aluminum foil, and it was successful. So, being a planner, I said the
Mhm.
next step is one that's about 100 square meters. So I had the opportunity, this is getting directly to your question, in the early parts of the teens, to write a proposal for Near Earth Asteroid Scout, which I partnered
Mhm.
with JPL,
Yep.
a planetary scientist there named Dr. Julie Castillo-Roget. And she wanted to go study near Earth asteroids and had a small camera, weighed about 1 kilogram. So we developed a small spacecraft that was the spacecraft was twice the size of the NanoSail D. So it was a 6U, okay, 12 kilograms. But the sail was just under 100 square meters, which is over 1,000 square feet.
Mhm.
Okay. And we built it, developed it, got it all tested, ready to go, put it in the spacecraft, and shipped it to the Kennedy Space Center to put on the Space Launch System in 2000 or 2020 is when we shipped it. I'm sorry. It sat on the rocket untended for 2 years while the rocket was prepped for launch. And then I was there in November of 2022 for the launch of Artemis 1, which is the Space Launch System rocket. And the rocket launched successfully and deployed the Near Earth Asteroid Scout spacecraft. We never got a chance to deploy the sail because the spacecraft never called home.
Mm.
It was supposed to activate when it was deployed. The radio was supposed to say, hello, I'm here. We're going to talk to it, check it out, and give the command to deploy. I even had what I was going to say when it was time to deploy the spacecraft. I was channeling Jean-Luc Picard with Engage. Instead of warp drive, it was going to be the sail. But the spacecraft never called home, and we don't know why not. So we never really had a chance to test that sail. Okay. But there was the flight alternative sail system was the Advanced Composite Sail System, which found a ride into low Earth orbit. And the team at the Langley Research Center flew that, and it's up there now.
Okay.
So the technology we developed for NEA Scout has been tested in Earth orbit, but it's not flying in interplanetary space. And then that gave birth to the mission I mentioned that was originally called Solar Cruiser, has a
Okay.
new name now, and it's really big. It's all right. Hold on here. That same thin material. It's over 1,000 square meters, so I'm edging my way up to the square kilometer, and it's over 17,800 square feet in area.
Okay.
17,800 square feet. So if you compare that to your apartment or your house,
Sure.
you get the idea of how big this thing is. It's about the same size as your local pharmacy. Okay, I mean it's big. So that's exciting. And I'd also like to say that the other big thing that changed is the big sail to go to Proxima Centauri that had
Okay.
to be extremely lightweight, and there was no material strong enough at that time. That is no longer the case. In 2004, in the UK, they discovered graphene,
Yeah.
which is a form of carbon. It's a single atom layer thick lattice of carbon atoms. It is strong enough to be the substrate of a square kilometer sail. The problem is they don't know how to build a square kilometer sail yet out of graphene. But now the material exists, and it did not exist when I put that plan together. So I'm optimistic.
Hmm.
Advances are moving ahead, and I think we're on our way to maybe after 2029 with the 1,000 square meter sail. I think we really could start designing one that's 10,000 square meters.
Okay.
So we're really on our way.
And again, thinking back less to your master's work and obviously you talk about the material science side there, but clearly lasers and beamed energy were a part of that. And one of the guest I had on the show about a year or so ago was Tom Carr, who headed up the directed energy office at the Pentagon until recently when he retired. But he was a very big proponent of again thinking beyond defense applications of directed energy. And I don't know if were you involved in the breakthrough starshot
I
stuff? Because
was.
okay,
Yep, yep,
because
yep. I had limited
I had
involvement because I was a
okay.
government employee, but I went to their meetings and was as a consultant for them. Yeah.
Could you say, I mean, because I had Avi Loeb on also a couple of years ago, and thinking about extreme materials and lasers. Obviously, we don't want to puncture our sail with the laser and all that bit, but a little bit of how you think about laser propulsion in amongst this set of let's say themes that need to come together to make this go right.
Sure, sure. Well, I mean, the drawback of a solar sail is that the sun gets more dim as you move away from it.
Right.
There's this thing called the inverse square law, which makes it really get dim.
Right.
Basically, what that means for your audience is if I'm at the Earth sun distance and I have a certain amount of sunlight on my sail, if I double that distance from the sun, I don't get half the amount of sunlight. I get 1/4 the amount of light. And so if I triple the distance, it's not 1/3 of the light, it's 1/9. I mean, it drops rapidly. So if you're going to continue to accelerate as you move away from the sun, your acceleration drops off rapidly because your light source
Right.
gets more dim. The logical way to fix that problem is to build big lasers
Mm-hmm.
and shine laser light on your sail so that you can continue to accelerate and not have to carry fuel. Again, that
Yep.
takes a lot of weight, it's inefficient. So that was talked about for years, but it was talked about in the context of the really big sails, like the square kilometer sail or one that might be 100,000 square meters instead of a million, and big laser stations that would be in space, maybe one near the Earth, maybe one near Mars, maybe one near Jupiter or something. Whereas the sail's moving out, you keep lining it up with a different laser to make it go faster and faster and faster as the laser light reflects from it. Now, Breakthrough Starshot, thanks in large part to the work at University of California, Santa Barbara, Dr. Phil Lubin, he realized that with miniaturization of spacecraft, you could get really lightweight spacecraft, think grams instead of kilograms, hundreds or thousands of kilograms in the future. And you could build lasers, solid state lasers now, which are basically fiber optics, a lot less complex than making lasers in the past. Lasers are approaching, I mean, they're hundreds of kilowatts now, if not up to ganging them together to get millions of watts. So he could see a future where you develop these big lasers and really small spacecraft, and then you could shine lasers on these smaller sails and maybe send a whole bunch of these little wafer sats to stars all over nearby space where they fly by, send pictures home, and we get data. So they started the project Starshot, Breakthrough Starshot, which is a great idea, but
Mm-hmm.
they would have to advance lasers, spacecraft, sail technology, all of that to get it to the scale that they need. And they made some progress, but
Mm-hmm.
that project has officially been put in dormancy. I don't know that it's been canceled, but it's on hiatus.
Yeah.
And that's really unfortunate because some good work came out of that. But I think in my opinion, it was too ambitious. I think the gram scale spacecraft, we're not anywhere close to that. The laser work, though, I think we're close to being able to have small payloads propelled by high energy lasers in space
Mm-hmm.
that could take small payloads to Mars in really short amounts of time. So I think within the next 10 to 20 years, if we focused on it, we could probably have laser propelled spacecraft sending small payloads all over the inner solar system.
Nice.
So that's a step to Proxima Centauri. It's that
Yeah.
little baby step, but it's on its way. Now the benefit is instead of a 1,000-year voyage, if you have a big enough laser system and you have a few of them, you could take my sail and get to Proxima Centauri in less than 100 years.
Mm-hmm. Mm-hmm.
Okay, so sunlight alone, deployed near Mercury, where the sun's really bright, 1,000 years. Deploy it, have laser systems, maybe under 100 years. That's
Mm-hmm.
exciting.
Yeah, absolutely. And this is a sort of a nice segue. Obviously we could talk for hours on propulsion systems, but you've written about a lot of other stuff, and last year you published in 2024 Interstellar Travel Propulsion Life Support Communications and the Long Journey, and you sort of do a deep dive into all the other things that we need to be concerned about, whether it's me going to Mars in Mr. Musk's Starship, or you on the solar sail to Proxima Centauri. There's a chapter on crew health, and again, this is something that we've touched a bit on. We had Matt Roberts on from the International Space Station National Laboratory talking about some of the sort of the experiments, the biologic work that they do there. We profiled Polaris Dawn and some of the radiation genomic stuff that has to happen. Sort of give us your sort of report card on where we are, because clearly space is tough. There's a lot of stuff out there that impacts our biology. We've begun to think a little bit about it, but where are we sort of on the scale? What do we need to get done that you think we're not getting done yet in terms of keeping us not just healthy, but sane on some of these journeys? Take us into that world.
Well, the book you mentioned is a technical monograph. It's the second book in a 3-book series. I was editor for that. All the chapters were contributed by experts in their field, in life support, communications, all these other things. So it's not a chapter that I wrote, but I am very familiar with the contents because in my career, I've dealt with several issues like that where I've worked with like Mars mission studies and moon studies and all this. We humans are really the weak link in space. And the debate of humans versus robots always rages on. AI is going to make that even more so. I'm of the opinion that you send the robots first and then you send the people.
Yeah.
Because I think we want to go. I don't think just looking at it on a screen is going to satisfy the human urge to explore and expand. And I think ultimately we have to go, which means we have to address the issues you just raised.
Yeah.
We have needed for years some kind of variable gravity research laboratory in space to figure out how much gravity is enough. We know that the astronauts aboard the space station who are only in microgravity, almost zero gravity, their muscles decay, their bones decay, there lots of redistribution of fluids in the body due to lack of gravity, and it basically is like advanced osteoporosis for the astronauts. And they have to exercise 2 to 3 hours a day to keep muscle mass, but there's really not much they can do about the bone mass thing without gravity. So there's been proposed various methods to have a spinning spacecraft to simulate gravity because the question is not known of how much gravity is enough. Do we have to have the full 1 Earth gravity to keep these processes from happening? Or would a third gravity be enough? Would a sixth be enough? The moon is 1/6 the gravity. Will they experience bone loss over long term on the moon? And at what rate? We don't know. But it seems like we need to do some experiments there to understand that. Also, all of the physiological processes that are affected by gravity, all the way to things you would have to worry about on a long duration mission with mixed gender crews. What if there's a pregnancy?
Right.
What if there's, whatever? You got to understand these things. We haven't done a heck of a lot with the gravity side of it. We are finding out and learning a lot about how to deal with the radiation.
Yep.
We know how to protect crews from that, but unfortunately, it just requires mass. The best way to shield yourself from radiation is to be in a lead-lined room. Lead's heavy, it's expensive to launch. So there are different people looking like electromagnetic shielding to deflect some charged particles, things like that. And then there's just the DNA damage that comes from that radiation. There's the psychology of people being in a tight space with each other for a long period of time. Going to Mars on a 3-year round trip, which is what it would be today, would be like you getting in your, just imagine you're a boomer and you're one of those big, Winnebago self-driving campers with 6 of your best friends and you can't leave for 3 years. um, I
Hmm.
don't know how that's going to
No,
work out. Friends
getting
or
into
no,
flights.
I
Yeah,
think there's going to be a problem with that. So
yeah,
there are a lot of issues we've got to work out.
right, right. You mentioned there, Les, about sending the robots first, and it got me thinking of, in between the robots and us, there's other stuff that, is being proposed that we send. I mean, Craig Venter is a big fan of sort of astrobiological experiments using some of, the tools that we have in terms of genetic, printing and all that bit. And it sort of gets us into that realm of, um, astrobiology on one front, and planetary protection on the other. And I know this is something you wrote a little bit about as well. Planetary protection, not just from, hey, Andromeda strain type stuff of what's coming down potentially that may be hazardous, but we could pollute other planets very easily if we do the wrong thing, whether that's playing around with microbes or whatever the case may be. Your perspective on sort of planetary protection in general, because I know the White House had, OSTP had some reports on this a few years ago, and how we have to be, kind of delicate about, where we tread, what we bring with us. And then thoughts on astrobiology initiatives in general. My next door neighbor until he passed several years ago was Barry Blumberg of hepatitis B fame, Nobel Prize fame, but he went on to become NASA's sort of the chief of the Astrobiology Institute there for a few years in the early 2000s. Love to get your perspective while we have you today on all things astrobiology and what we should be working on there, because I know that's kind of been a hit, not hit or miss, but something that let's say the funding has kind of waxed and waned over the years. And again, love to have your perspective on these topics.
Sure, sure. Well, of course, we want to protect our biosphere from any microbes that might come back. So the whole
Right.
notion of making sure we contain samples from places where there might be life need to be real careful. Most of the universe is dead. I mean, it's just dead and it's going to stay dead. In fact, as we look out into the solar system, we find places where there might kind of sort of look like there might be life, but the vast majority of places are like the moon, blasted by radiation, totally dry, just hostile to life, ready to kill you. It's like Jack London's The Call of the Wild, only 100,000 times worse, right? The Yukon was trying to kill the protagonist in that book, and when you get in space, nature's trying to kill life at every opportunity.
Yeah.
So the vast majority of places we go are dead, and they will always be dead unless we take life there. And I think we can do that responsibly, and we should. I think it is a moral imperative to spread life beyond Earth. However, I think if we do find another world that has its own biosphere, we don't want to contaminate it. I think we want to be really careful. We want to study it. We don't want to have a reverse Andromeda strain where we take life here and it takes over or is hostile to any life that we find there. And we got to be real careful. And so it's sort of like Star Trek's Prime Directive, right?
Mm.
You don't interfere. So generally speaking, I don't worry about what we take to the moon. I'm not going to worry about what we take to asteroids or most other moons or planets in the solar system because they are almost certainly dead. Now, Mars maybe had life or has life. Enceladus, maybe. Europa, maybe. So we got to be careful there. We don't want to contaminate it. But if we determine that it's just a dead world and there's something we can do there to bring life there and flourish, I'm all in. I think it's the right thing to do. So it would be, in my opinion, a cosmic moral error, as rare as we think life may be, and especially intelligent tool using life, that if we did not spread it beyond the planet that gave it birth. Because I think in this big universe, it is mostly a dead universe, and life is good.
Yeah.
Just look at the love you have for that significant other in your life or a child. Mozart symphonies. Yeah, we got our warts, but life generally is good. And I think we need to expand out and spread life as far as we can.
Um, let's talk about a couple other cool projects that you've been involved in over the years, and then we'll loop back again to SDI and all that stuff. But 2023, I read this piece. It's entitled "Planetary Sunshades for
Oh
Solar
yeah.
Radiation Management," and obviously, the whole area of geoengineering is kind of, I guess, contentious nowadays. And I don't like going onto my Twitter feed anymore because someone's always talking about chemtrails and this, that, the other thing. But over the years, we have smart people like you have thought about everything from how we diminish the amount of radiation coming down. We used to have this Project Storm Fury at NOAA on how potentially we can modify hurricanes to make them less dangerous, and cloud seeding and all that bit. I know the UAE has a lot going on in terms of that, and sort of get a little more rain flow in the in the middle of the desert. But I like geoengineering. I like these concepts. What were you thinking about back in 2023, and some of where you'd like to see that whole area go in terms of cooling the planet down with the
Well,
parts of technology?
it's not just in 2023. I'm still
Right.
involved with that. I'm
Cool.
kind of supporting a group called the Planetary Sunshade Foundation. Your
Nice.
listeners can look them up, and other groups that are looking at this. The idea is take essentially the solar sail work that we've been doing and the square kilometer sail, and instead of using that to go to Alpha Centauri, flying a whole flotilla of those at a place called the Lagrange point, the Earth Sun Lagrange point.
Okay.
And that is a region of space, roughly speaking, where the sun's gravity and the Earth's gravity kind of balance out, and
All right.
you can put spacecraft there, and with very little propulsion, they can always remain between the Earth and the sun as the Earth goes around the sun. Normally, a spacecraft that's at a different distance from the sun has a different orbital period, and at times it'll be on the other side of the sun from where the Earth is. But things that are at L1 always remain between the Earth and the sun because of that balance of gravity and a little bit of propulsion. So if you were to put a flotilla of these solar sails, of whatever size they may be, you could reduce a little bit of the sunlight that reaches the Earth, and that would reduce the heat input into the atmosphere. So there's less heat to be trapped by the
Mm-hmm.
excess greenhouse gas. In theory, and some modeling has been done by climate scientists, this could reduce and offset some of the temperature rise that we're experiencing and anticipate to experience from climate change. Now, there's a lot of concern about geoengineering. I share the concerns about geoengineering in the biosphere because
Yeah.
historically we do things and there are unintended consequences that
Right.
happen. And if you start, putting sulfates in the upper atmosphere to scatter light and suddenly it stops raining globally or something, I don't know what it
Right. Right.
would
Right.
be,
Right.
some unintended consequence. It might be disastrous and take a long time to undo. And I'm not saying that's what would happen. I'm just saying we don't know
Right. Right.
everything that will happen. But these are out in space. They're not in the biosphere.
Mm-hmm.
And as you're going to be building it up slowly, because you can't launch it all at once, and as you're putting these out there, you'll notice incremental changes. And if something negative starts happening other than just the temperature reduction, you basically just fly them away from L1 and you're back where you were when you started with the normal sunlight reaching the Earth. So you don't have to worry about it. The scale is big and it's going to be expensive. Um, but I would argue that the climate engineering we're doing right now with fossil fuels is far bigger, and we've spent far more money doing that than it would cost to put the sunshade out there
Oh
to
yeah.
mitigate that.
Yeah. Absolutely.
And I don't propose the sunshade as a reason to not go carbon neutral and not become more green. I
Mm-hmm.
think we aren't going to be able to come green enough fast enough. And so I think the sunshade needs to be in addition to trying to be carbon neutral.
Yeah.
Put the sunshade out there to buy us time while we get to carbon neutral. So yeah, we could do that. Do we have the tech now? No. Just like we
Mm.
don't have the tech to go to Proxima Centauri. But I think it's a lot more doable
Yeah.
than going to Proxima Centauri because it's close and we could build very large sails fairly soon and
Mm-hmm.
start deploying that flotilla. So I think it's worth considering, and it needs to be on the table.
Yep. Yep.
That's my argument. Don't rule it out. Just needs to be in
No.
the discussion.
Yeah. No, and again, talking about degrees of doability, this sort of brings us full circle. And just to sort of like lay the groundwork for this, clearly, a couple of months ago, President Trump, started talking about the principle of Golden Dome and missile defense. The Netflix series House of Dynamite has been sort of all the rage, talking about, you know, like I say, the limitations to where we are currently with shooting a bullet with a bullet. And again, this brings me back in 1983. I remember it, just like, a couple of the key points of in my life when President Reagan came on TV. And, I was a kid of the Cold War, and, nuclear war scared the hell out of me. But I was thought, if you create things that are more dangerous or could destroy missiles faster than a missile, like lasers or particle beams or whatever, I'm like, hey, I'm a big fan. We profiled Tom Carr from the Pentagon, and he talked in the kilowatt range. We had Heather Wheatley and Andrea Krieger on from Lawrence Livermore with the National Ignition Facility. They're in the megawatt range now with these things. Yeah, we're not there yet, but this is one that I would love to see done because I hate nuclear weapons. And if things come faster and we can make lasers that come with the rate and the intensity that they need to be, I'm all for it. And I'd love to, again, just get your perspectives on where we are in sort of different areas. I mean, I know I don't think at least they ever built the tungsten rod concept and rods from God and all that. But, where do you think we're going in terms of Golden Dome and potentially applications of some of the stuff you were working on back in the 80s to make this a little safer, let's just say, for all of us?
Well, I just finished watching House of Dynamite, and I think that, it's correct that hitting a bullet with a bullet is really hard. And in the movie, they only launched two of the 50 total interceptors that
Right.
we have to try to take it out, and that's probably not enough. But
Right.
I think I'm not directly involved with the current effort of Golden Dome, but I know people who are. Remember, I live in Huntsville. This is Missile Defense Agency is
Yep.
10 miles from my house right here, right?
Yep.
And we're going to be getting Space Command and all that's coming to town to be here with NASA and others. And I've worked off and on from my GRC days with the Space and Missile Defense Command for the Army, who's also
Yep.
involved in Golden Dome and everything
Yep.
happening. So looking at that, I think the early efforts are going to concentrate more on the kinetic kill vehicles, the bullet with a bullet. But I think they would be remiss if they um, don't also consider all the advances we've had in high energy lasers and particle beams, which are
Yep.
the two elements that I worked on early in my career. Because the advancements in lasers in particular that you mentioned are huge,
Yeah.
huge. 30 years ago, when I was working this, 35 years ago, to get the class laser that you're talking about, the National Ignition Facility, you had to basically have an apartment building sized facility using hydrogen fluoride gas to get the lasing effect to make the lasers that could be possible. And putting that in space just seemed totally impossible. Now it's all solid state. You can do phase lock and gang them together. You can power them with electricity from solar power potentially. So I think we are close, I think, to being able to have a death ray, right, with lasers to be able to take out some of these things. Is it in hand? Probably not. It is for things like drones. Yeah, the Army's developing high-powered lasers, 65 kilowatt lasers to take out drones. That's great.
Mm-hmm.
Space and missiles is a lot harder. It's going to need more power, but I don't think we're that far away. So I think concentrating on, the known technologies first, if you want to field a system quickly, is the right thing to do. But if I were managing the program, which I'm not, I'd put like 10% of my resources on some of these other things because I think it could really pay off and make it a lot easier and a lot more effective in the long term.
Yeah.
And by the way, I don't see a problem with defending against it. Like because the scenario that was in House of Dynamite is the reason you want to have something like
Right.
this.
Yeah.
If a rogue state like North Korea or Iran launches a missile or two, we should have the ability to take that out.
Yep.
We can't stop 1,000 of them coming over the poles from Russia. probably. Can't get them all. Some will get through.
Not with 50 interceptors.
Well, I mean, even if we had far more than 50, right?
Right. Right.
Something's going to get through, which means, a full-scale nuclear war is still unthinkable.
Right.
But some rogue state doing something like in that movie, I think it's a disservice to the public for us not to have a way to take it out. Personal opinion.
100% agree with you on that. No, it's again, I appreciate your insight just because, the fact that you've gotten near these technologies and understand the doability issues and what's required. But I appreciate your insight.
Well, see, I've lived my career on the edge of engineering feasibility.
Right.
NASA is a pretty conservative culture, as is the military for the large part. And they like to build things they built and they understand and they know how to do. And the engineers who work there are like building things. And I kind of think of engineering reality as like a tabletop. And the closer you get to the center, the more you've done it, the more you understand it, the more traditional it is. And when you get toward the edge, it still can be done, but there are more unknowns in how to engineer it and you have to figure it out, right? And you get off the edge and you're not in the realm of possible anymore. You're into science fiction. And so I've really worked hard in my career to not be at the middle of the table. I like walking the edge. I don't want to walk off the edge, except in my books, right? Because I obviously want people to read my science fiction novels. But in my career, I've tried to stay on the table, but I have intentionally put myself toward the edge of the table.
Yeah. We need people like you there with the great minds. And again, this has been a fascinating discussion, and I appreciate you, taking us through all these themes. What's up next for you? Because I mean, obviously you're writing both on the nonfiction and the fiction front, but you're clearly keeping your feet wet in many of these areas and getting involvement with the Starshade or the Sunshade project. What should we look out in terms of you, in terms of 2026, other public facing stuff that's coming up that we should know about while we have you today, and anything else that you'd like to talk about while we have you?
Well, that's great. Well, thank you for your interest. I just retired from NASA in August, and so this is all fairly new to me to be on the other side, but I formed my own company, Infinite Frontiers Consulting.
Nice.
And I'm already getting a few clients from space
Excellent.
startups, companies that have some VC funding that want to understand a little bit more about space and get some of my experience to go to that. So that's exciting. In fact, I had barely left NASA when I started getting emails, "Hey, are you available?" And I was really flattered for that. I got to be careful or I'll end up not being retired. I'll be working more hours than I did. So I'm going to spend about half my time writing. I've got a book for Princeton Press that'll be out in about a year and a half or a year that I'm almost finished with, that talks about how we can use space technology like the sunshade and other things to help solve energy and environment problems here on Earth. I've got a new novel just came out November 4th, science fiction novel about Pluto, finishing Ben Bova's series, the Grand Tour series. Got a few more contracts in science fiction. I love doing that. But I think Infinite Frontiers for the forward-looking technology thing is where I'll concentrate a lot of my efforts. And I'm also an advisor to an investment banking firm that is looking at space technologies, and that's League Advisors have me on board there. And so I'm going to have my finger in lots of places trying to help get this space revolution moving faster, but mostly from the non-government side now. It's going to be from private companies who I think are doing a lot of the innovating, and that's exciting. I think those of us who grew up in the 60s and 70s envisioned this private space time happening a lot sooner than it has. And I'm glad I still have a few miles left in me to get involved and help make that happen.
That's awesome. That's awesome. And I'm excited. Again, I wish you the best in your retirement, but in many ways, I wish you don't retire too much because clearly there's so much happening. And it's going to be great to have you involved in all these types of initiatives. We'll put the link as not just your website, but also specifically to the Infinite Frontiers consulting component as well, so people can check that out. But Really impressive, Les. Really impressive career. I wish you the best with everything you do as we get into the new year, and I look forward to your continued writing on these various topics. And again, we'll also put a link to your Amazon page, and so people can check out all that. But really impressive work. Again, for everyone out there that is going to be listening to this episode of the show across the various podcast networks, or who will be watching on the YouTube channel. You've been spending time with Les Johnson, the recently retired chief technologist, NASA's George C. Marshall Space Flight Center. Check out the links to Infinite Frontiers Consulting, also to Les's website and Amazon page. But Les, again, I want to thank you for, again, taking the time out of your schedule to talk to us for a little while about everything you've been up to. Thank you for everything you've done to move this amazing future for us all forward. And as we like to say on our show, thanks for helping to create a better tomorrow for all of us via what you do. Really an awesome story.
Well, thanks for having me on. And I have to admit, when I'm in discussions like this, I just think back to the 12-year-old mini me in Ashland. And I just have to say, I feel really blessed to have had the opportunities to do what I've done. It's been great, and I've enjoyed all of it. And I just have to say, I just feel very, very fortunate to have been able to make a contribution.
It was awesome having you. Really great having you.